Okay, people are getting settled in. Welcome back. Our fourth presentation is presented by Jeffery Ling from Palo Alto Senior High School in Palo Alto, California, and Helen Jiang, Henry M. Gunn High School, and also in Palo Alto, California. It's entitled Novel Diagnostic and Prognostic Utilities Integrating Clinical and Molecular Findings to Manage Necrotizing Enterocolitis in Neonatal Care.
Hi, I'm Helen.
I'm Jeffrey.
And before we begin, we'd like to thank the Siemens Foundation for giving us this opportunity to present. Today, we will be presenting our project titled Novel Diagnostic and Prognostic Utilities, Integrating Clinical and Molecular Findings to Manage Necrotizing Enterocolitis in Neonatal Care. Necrotizing enterocolitis, or NEC, is a devastating inflammatory disease that affects at-risk premature newborns in an unpredictable manner. It is one of the most common life-threatening diseases of the newborn, with a prevalence of 5 to 10% among low birth weight infants and a death rate ranging from 15% to 30%. Survivors are with a 25% incidence of severe neurodevelopmental impairment. NEC and neonatal sepsis can resemble each other, and together they constitute a 40% incidence among low birth weight infants. The high cost of care for NEC is mainly due to the lack of effective diagnostic and prognostic utilities, so many patients are being overtreated in an attempt to mitigate this misdiagnosis. Using clinical parameters like patient demographics, laboratory tests, radiographic analysis, medical history, and physical exam, we have developed a NEC prognostic algorithm that risk stratifies patients into low, intermediate, and high-risk groups. However, as you can see, the clinical parameters cannot adequately predict the NEC outcome among the intermediate group. Therefore, we hypothesize that molecular profiling, in addition to clinical data, will improve neonatal care. Urine plays an important role in clinical diagnostics. 70% of urine proteins and peptides originate from the urogenital tract, while the remaining 30% originate from the circulation. About 900 liters of plasma flow through the kidneys each day, and 150 to 180 liters of this plasma is filtered through the glomerulus, or the primitive urine. About 99% of this primitive urine is then reabsorbed through the renal tubule, and the remainder then exits the kidney via the ureter into the bladder. One-dimensional HPLC separation is sufficient for the analysis of over 1,500 urine proteins and over 100,000 urine peptides.
Proteomic-based biomarker discovery is an emergent high-content biomarker screening approach. This slide diagrams a typical liquid chromatography mass spectrometry-based biomarker discovery process. The data reduced from LC-MS can be subjected to downstream statistical learning to mine for biomarker peaks, which will then be subjected to MS-MS protein sequence identification. Future orthogonal assays, including quantitative mass spectrometry and antibody methods, are needed for prospective validations. Our data-driven biomarker program is like finding a needle in a haystack. First, vast amounts of LC-MS spectral data need to be reduced through peak finding, peak alignment, and peak indexing. The output of data processing is essentially a P by N table in which each of P peaks has been quantified in each of N study samples. This data matrix can be subjected to transformation, normalization, and supervised or unsupervised analyses suited to the experimental design to search for differential spectral features for future orthogonal assay validations. Today, we will describe two examples of integrated algorithms to demonstrate our data mining process. This diagram shows a flowchart of steps for our first algorithm in peak detection and analysis. To locate spectral features, our algorithm maps spectra onto a uniform mass-to-charge ratio axis using linear interpolation to ensure that they are directly comparable. Spectra from each group are then averaged to give a single average spectrum for the dataset. An area under the curve, or AUC filter, is applied to the composite spectrum to calculate the value of a hypothetical peak at every location in the spectrum. Each local maximum in AUC is recorded as a peak location. An F-test score provides a means to control the false discovery rate by including only peaks with signal greater than measurement error. the algorithm normalizes spectra using peaks with high signal content from the f-test and assigns weight to each of them inversely to their variance across spectra. After normalization, the algorithm computes a chi-square statistic to remove poor quality spectra. So taken together, we have integrated an algorithm to improve the accuracy and efficiency of the mass spectral peak analysis, which locates proteins across spectra, measures their abundance, subtracts baseline, excludes irreproducible measurements, and computes normalization factors for comparing spectra. In our second algorithm, we set out to develop a method to quantify, normalize, and compare complex label-free proteomic data to search for urine protein biomarkers. We used the normalized spectral index, SIN, normalized to both protein length and total spectral intensities. In SIN, we include the spectral count, or number of MSMS spectra per peptide of the protein, and unique peptide number. We also include fragment ion intensities as a feature easily extracted from typical MS data. The spectral index, SI, is the cumulative fragment ion intensity for each significantly identified peptide, including all of its spectra for each protein. Here, SC is the spectral count for each peptide, I is the fragment ion intensity for each spectral count for each peptide number, and PN is the number of peptides identified for that protein. Adding the fragment ion intensities and dividing by all proteins' spectral indices in the sample, as well as protein length, normalizes and quantifies each protein with respect to all samples. Among the identified urine proteins as NEC biomarkers include several that may be of particular interest. Their biological functions are related to the NEC hypothesis that includes bacterial invasion of the newborn gut and the inflammatory cascade that results in coagulative necrosis. We found proteins, including apolipoprotein, complement factors, angiotensinogen, and cystatin. Perhaps most interesting is CD14, an integral part of the innate immune system and has been implicated as causative of NEC. CD14 urine abundance differentiates between NEC medical and surgical groups, as well as neonatal sepsis. However, close examination reveals that CD14 expression does not unambiguously distinguish between NEC M and S groups, demanding that a panel of additional markers work in concert to achieve the desired sensitivity and specificity. Among the identified urine peptides as NEC biomarkers include the nested uromodeling peptides, collagen peptides, and shown here, the 3 nested fibrinogen alpha peptides. These whisker plots summarize the results of the quantitative mass spec validation in new neonate NEC MNS samples. Mann-Whitney's test indicated the strong significance of separation between NEC MNS subjects. As described in previous slides, clinical stratification modeling suggests that clinical parameters alone are inadequate for NEC outcome prediction. To improve diagnosis in all patients, we used ensemble data mining methods to combine clinical and molecular biomarker classifiers to improve NEC outcome predictions through practical algorithms. We used the clinical parameters of patient demographics, laboratory tests, radiographic analysis, medical history, and physical exams, and combined with the 3 urine peptide fibrinogen markers to improve NEC outcome prediction. As seen here, all of the patients can be prognosed correctly with the right outcomes using the multivariate models developed upon the integration of clinical and urine peptide biomarkers.
So we have several take-home messages from the study. First, urine is a rich resource for biomarker discovery and improving neonatal care. And integrating both clinical and molecular findings is an effective approach for NEC outcome prediction. We are continuing to add in more clinical and urine proteomic data into our database, and we have 2 objectives. Our first objective is to develop antibody-based biosensors and MRM quantitative mass spec assays. Microfluidic chip is being developed in the lab, and here are 2 examples of the design for a microfluidic chip. A microfluidic chip can be used, and signals like those of the antibody conjugated nanogold particles can be found. And using a smartphone like an iPhone or an Android, you can take a picture of these signals and send for the cloud-based computing to allow point of care for NEC. Our second objective is to use these assays for the clinical trial of the urine utilities. Future electronic medical record and molecular data can be used to further refine and improve our algorithm and data model. Finally, we'd like to thank the NICHD and the Neonatal Research Network for compiling a lot of neck subject samples. We'd also like to thank our Stanford mentors, Dr. Sylvester and Cohen, for their guidance. Finally, we'd like to thank the Siemens Foundation, College Board, and the George Washington University for giving us this opportunity to present. Thank you.
Okay, and time code is 01.
Yeah, it is a cool picture.
Hey, Dr.